Hello everyone, welcome to today's presentation. Myself Bhavani Shankar and today's presentation is on mechanics in biomedical and materials engineering. In this presentation, we will dive into the fascinating world of mechanics and its application in advancing healthcare and technology. Overview of this presentation is that this presentation will explore the applications of mechanics in both materials engineering and biomedical engineering, highlighting the synergies between these fields and their contribution to healthcare and technology. Now we will discuss the mechanics in materials engineering. Mechanics of materials engineering is that how the materials react to external forces and loads and composing attributes like strength, elasticity, and toughness. These are the mechanical properties of materials. First is strength. It measures a material's capacity to endure applied forces without breaking or enduring permanent deformation. And the second one is elasticity. It determines a material's ability to revert to its original shape after experiencing external deformation. And the third one is toughness. It evaluates a material's capability to absorb energy and undergo plastic deformation before fracturing. Mechanics plays a pivotal role in tailoring materials for specific application across industries. For instance, in aerospace, automotive, and structural engineering, materials are engineered with precise properties to suit requirements for aircrafts, component, vehicle safety system, and robust building structures.
Hello everyone, my name is Karthik Gelur. I will tell you more about biomechanics. Now let's discuss on the topic of mechanics in biomedical engineering. So, as the definition of biomechanics suggests, biomechanics is the study of mechanical behavior of biological systems, including the movement, the structure, and the functioning of living organisms. Also, the study of mechanical behavior of biological systems comes under the mechanics of biomedical engineering. Now, biomechanics encompasses the analysis of forces, stresses, and strains within the human body and the other biological entities. For example, musculoskeletal mechanics, which includes the study of the mechanical properties and functions of musculoskeletal system, including bones, muscles, and joints. Also, cardiovascular mechanics, it investigates the mechanical forces and dynamics involved in the blood flow and heart function and vascular health. Also, we have cellular mechanics, understanding how cells respond to mechanical stimuli and forces and their role in tissue development, repair, and disease.
And now we will discuss about applications of mechanics in materials engineering. And the first application is in aerospace. Mechanics plays a crucial role in aerospace industry by facilitating the design of materials with optimal strength to weight ratios. Lightweight materials such as carbon fiber, composite, and titanium alloys are utilized to reduce the overall weight of aircraft components without compromising structural integrity, resulting in improved fuel efficiency and performance. And the second one is in automotive. Impact resistant materials for vehicle safety. Mechanics influences the development of materials that can absorb and dissipate energy during collision, thereby enhancing vehicle safety. And the third application is in structural engineering. Mechanics is essential for designing materials capable for supporting structural loads and resisting deformation under various environmental conditions.
So now let's move to applications of biomechanics. And first application is mechanics used in tissue engineering. Now the first point is role of mechanics in tissue regeneration. Mechanics guides the design of scaffolds and biomaterials for tissue engineering application to mimic mechanical properties of native tissues and promote regeneration. So the main property is that it is helpful in tissue regeneration. And now second point, design of biomechanically compactable scaffolds. So mechanics influences the fabrication techniques and structural design of scaffolds to provide mechanical support and cues for cell growth and differentiation. So it basically helps in designing biomechanically compactable scaffolds. And the other application is application in regenerative medicines and organ transplantation. It also plays a role in organ transplantation. So it is mechanics driven tissue engineering approaches hold promise for repairing damaged tissues, regenerating organs, and developing alternatives to organ transplantation. Other application of biomechanics is the mechanics used in the drug release systems. It having various mechanisms, one of which is controlled release mechanism. This mechanism is utilized to design drug delivery system that control the release rate and distribution of therapeutic agents over time. Also, other point is targeted delivery systems, which is mechanics guides the development of drug carriers and nanoparticles that can target specific tissues or cells within the body. These are helpful nowadays very much. Biomaterials hold the key to unlocking the body's innate potential for healing and regeneration, paving the way for future where medicine is personalized, precise, and profoundly impactful. With this quote, I would like to end this part of our video, which is very related to the use of mechanics in bioengineering and materials engineering. Now let's move to the next part. So the next part of this video is related to human robot collaboration, which is very important nowadays. Every industry needs requirement of efficiency, which can be provided by human robot collaboration. So let's see what is in the slides. With the human robot collaboration, we can solve many problems. The problems of space, the picking problems, the momentary problem, the sorting problem, the dirty jobs which no one wants to do, which can be performed by the robots. And now let's see some of the examples of human robot collaboration which are going nowadays. First one is carrier board for robots. Second is autonomous mobile robot, and the third is legged robot quadruple. This is not a very easy task to create robot human collaboration. We face many challenges. First one is the hardware challenges we face. A mobile robot is composed of multiple sophisticated components. The availability of them is a big issue. The components include motor, actuator, supply chain constraint, modular design, sensors, cost versus reliability, ever evolving, industrial grade safety certification, motor controller, battery, reliable communication, antenna placement, AP placement, latency, functional safety certified processors, and also the other issue is which is above all, each of them involving tremendous rate, which one to use. We are not able to decide which one to use. This is a major issue. Now next move to software issues.
As my friend told about hardware challenges, now I will discuss about software challenges. A mobile robot is processing a huge amount of data and making decisions in every millisecond. Okay, first is sensors and sensor fusion. It means processing a large amount of data, noise, and dust. And the second is edge cases. It is just a journey from 98% to 99.5%. And the third is localization. It means we have to create dynamic environment when to update the map in a read with limited features. And fourth is mapping. Mapping is just an art of science. And second last is self-navigation. Self-navigation. Behavior around humans, blind spots, and tight areas is just a self-navigation. And the last is planning. Planning is dynamic objects around other robots.
Human robot collaboration isn't just about efficiency, it's about enhancing humanity's capacity to care, innovate, and transform life. With this quote, I like to end this part of the video, the last part. Thanks for watching, and what our friends say.
Thanks a lot for watching my video. I hope you will like it and thank you.